So. Oh yeah. That was like the third day of class.
Okay, good morning everyone. Good morning. Alright, let's get going. I'm going to solve two problems. I'm going to keep an eye on the clock. We will try to wrap it up by 12:25, 12:30 max. Okay? Alright. And what I'll do, what I'll be doing is, as I'm solving the problem, I'll tell you in what ways this problem can be modified as an exam problem. Okay? So that you are aware of the possibilities that exist within each problem. Right? Alright, so here's the problem. And they are fairly gentle problems, but you can see they can become quite a beast with certain changes. So here is one. We have a flat plate. Total length of the plate is, I think, 0.03 meters. The thickness of the plate is 100 millimeters, 10 millimeters. I'm sorry. On top, you have fluid flowing past. At U infinity of 5 meters per second. T infinity is 44 Kelvin. Okay. Then the bottom is open to very large surroundings. And the air on the bottom surface is very still. Okay, so there is no bulk motion of any kind available. There is no thermal conduction can be ignored on the bottom face and so on between the surrounding, through the surroundings. Temperature is given to us, each surrounding, 2550 Kelvin. Okay. Temperature at the top surface of the plate, I'll call it as T suffix capital T. This is given to us as 460 Kelvin. This is the average temperature throughout the length of the plate. Okay, so held the constant. Temperature at the bottom is not known to us. Things that we need to find out are the following. Some information is given regarding the flow. So for the fluid, Kf is 0.0284 watts per meter Kelvin. Then you're told that nu is equal to alpha. Is 1.725 10 to the power minus 7 meters square per second. And then you're told that the critical Reynolds number is 5 times 10 to the power 5. You're told that there is no transition region, which is kind of not reality, but we will assume it to be the case for this problem. So the flow transitions abruptly from laminar to turbulent. It doesn't happen in real life, but it's fine. The flow transitions abruptly And here are the Nusselt correlations for laminar and turbulent flow for constant uniform temperature. The two situations that we've seen is uniform temperature of the surface of the plate. The other situation is uniform heat flux where the temperature changes. Okay, so for this I have Nu x laminar is 0.332 or Ex to the power 1 by 2, Prandtl number to the power 1 by 3, and then something similar for turbulent. Is 0.029 or Ex to the power 0.8 PR to the power 1 by 3. And things that we need to accomplish in this particular problem. So first is obtain the average or the bulk heat transfer coefficient. That's the first thing. Second thing, obtain temperature at the bottom of the plate, and then the last one is obtain the thermal conductivity of the plate. For the plate, we are assuming there is no heat generation and so on. So steady state. Q dot is equal to 0. Ways in which this problem can be modified. First thing is, we need not have a transition from laminar to turbulent abruptly. I could have a laminar region, a transition region, and a turbulent region. The laminar critical number for laminar to transition will be given as 5 times the power 5, and from transition to turbulent, that will typically also be given in that particular case. Okay, so that's one thing. Second thing is, this need not be equal to 0, it could be positive or negative, depending on what is required of the problem. Third thing is, this need not be large surroundings, this could be a finite sized room. Fourth thing, I could have fluid flowing past the bottom of the plate. All of these things can happen in this one particular problem. Once again, okay, just to repeat myself, on camera, I can have flow on the top surface of the plate. Okay, that's one thing. The second thing is, I don't need to have an abrupt transition. I could have a nice, gentle, smooth transition from laminar to transition to turbulent on the surface of the plate. Okay. Third thing is, Q dot need not be 0, so you'll have heat diffusion equation coming into play in that situation. And you could probably have boundary conditions as the surface temperature at the top and surface at the bottom. Those would be the constants could be found out that way. Then you could have fluid flowing past the bottom surface as well. And the bottom surface exposed to finite surroundings, which means you'll have to bring in the radiative resistance networks. Okay, so these are the things that can change, but nothing earth-shattering. I mean, we have handled all these kinds of cases before. Alright, so let's go for this problem here, step by step. Obtain the average heat transfer coefficient. Because you're told both laminar and turbulent correlations are given, there's a high chance that some portion of the plate might have laminar flow, the rest of it might have turbulent flow. Okay? So to figure that out, we need to find out the critical length along the plate. So at x is equal to x critical, here is my x-axis. Y-axis. X is equal to x critical. RE is RE critical. And so let's figure this out. So 5 times 10 to the power 5 is U infinity x critical by nu. U infinity is 5 meters per second. Nu is 1.725 10 to the power minus 7. So this gives me the following value. X critical, solve. X critical is 0.0172 meters. Okay. So which means from 0 to x critical flow is laminar. And from 0.0172 all the way to 0.03, which is just going to be turbulent flow. Total length of the plate. Okay, does this make sense to everybody? So we need to calculate the average heat transfer coefficient or the bulk heat transfer coefficient. This could also be given as bulk. We looked at it before, but I just want to label it so that there is no confusion. Average heat transfer coefficient by definition is H bar is for a flat plate, okay, because we are assuming that the thickness is known to us, they cancel off. So this is 0 to L. H dx, where H is a local heat transfer coefficient. H is related to the Nusselt number. And I want to point out some terminology differences between the way I am solving the problem and what you have in your book. Okay? So here is what I mean to say. It's actually become much more smoother once I banged it down. Okay, so here is what we say. NUX is the local this is also what the book uses. No changes there. NUL is the average Nusselt number that I use we use this in class. This is the same as what your book calls NUL with a bar. Okay? It's all the same thing. So this is the book. That's the same thing. If I have to calculate the Nusselt number at the end of the plate, this is my terminology. Okay, this is the Nusselt number at the end of the plate. And the book calls this as NUL. Be careful. Okay. So you are welcome to follow any one of these ways of labeling things. As long as we have the right answer, we don't have an issue. But I'll be sticking to what I have written down here, okay? Just so that we are all clear. And then we're going to make use of this because H is going to change on the laminar region. It's going to be dependent on the Nusselt correlation to laminar flow. In the turbulent region, likewise. I have to rewrite everything in terms of the Nusselt flow. So H is NUX times X by, I'm sorry, by KF by X. Okay. All right. So H bar, we split it into two pieces. 1 by L outside. Integral from 0 to X critical. You're going to make use of the H laminar correlations, which I'm going to write in terms of the Nusselt number. Times if you had a transition region, you would have a second integral, and then the turbulent Nusselt number correlation will be coming into play. We don't have that here for our problem. NUX turbulent times KF by X dx. Does this make sense to everybody? Okay, very, very basic stuff. but we still have to do it. And all we have to do is plug and check, okay? Which is a good part of it. So H bar, Kf is a common factor, so take it all out. So Kf by L, and this is 0 to 0.0172 meters. NUX laminar, so 0.332. The Reynolds number written as a function of x is u infinity x by nu whole to the power 1 by 2. Prandtl number, and then don't forget the factor of x which is in the denominator there, that makes a difference to the integral, plus same idea all the way to 0.03, and this is 0.029 u infinity x by nu to the power 0.8 PR to the power 1 by 3 dx. Alright. So one can solve this integral. I'm not going to go into the details of it. There is an x here, there is an x to the power half. So this entire thing gives me an x to the power minus half. Okay, then I have x to the power 1, x to the power 0.8, so I'm going to have x to the power minus 0.2. Perform the integration. We can do this. Substitute everything. H bar ends up as the following. It's 1000.2, it's pretty high. The culprit mostly being the turbulent region, which is going to increase the heat transfer coefficient. Alright, so that's the first part of the problem, obtain the average heat transfer coefficient. One could also say, okay, because I know the surface temperature of the top surface of the plate, what's the convective heat rate? I could calculate Q convection. This is the average convective heat transfer rate, not the local value. Okay, so this is the average rate. It's H bar. A times. I'm not told anything about the surface area of the plate, so I could perhaps calculate the convective heat flux, the average heat flux. So that's done. Then we look at the second and the third part of the problem all in one go. Okay? Many different ways of solving this problem. Here is one particular way. I always like to perform surface energy balance so that it gives me a clean idea of what are the people at play, what are the things that I can kind of ignore. So first, and as I mentioned, these are your free body diagram counterparts in heat transfer, so very important role. I don't know the direction of heat transfer, but I can hazard a guess. The bottom is pretty hot, 2550 Kelvin is no joke. So my great suspicion is that it's going to be heat transfer from the bottom, passing through the top, and then convection out. Okay. We don't know. It's completely fine if you assume it. There is no other form of heat transfer other than radiation at the bottom of the plate, so this is just Q radiation. Then there's going to be Q conduction, and here is y is equal to 0, y is equal to 10 millimeters. This is Q conduction. Right? Y is equal to 0. I want to make the distinction, and then we can have other arguments on the conduction. Then I have this is entering the top control surface, and it becomes Q conduction at y is equal to 10 millimeters. And goes off as it could also be possible that the top surface is open to large surroundings, you could have radiative heat transfer coming in. Or it could be open to a finite room, you're going to have a resistance network. Okay? Or you could have a shield and then a finite sized room, which means that you're going to have a 3-surface problem of some sort. Or a 2-surface but with more number of nodes. Okay? Now, because of the fact that there is no energy generation, and we are at steady state, there is no rate of change of the temperature as a function of time. We know from conduction heat transfer that if this is the situation, then the conductive flux at this surface at y is equal to 0 has to be the same through all parts of the finite sized body. Okay, so this tells us that you have steady conduction we have a linear temperature profile. One can use the heat diffusion equation to figure that out. And so Q conduction at y is equal to 0. If E dot G was 0, all this would be gone. I cannot make this assumption. Okay? And so from common sense, Q radiation is equal to Q conduction is equal to Q conduction. Energy balance. Alright, and then we just make use of large surroundings. So if that is the case, then Q radiation, we proved this in one of the problems some time back. For large surroundings is sigma A epsilon and then T please notice the direction of heat transfer has changed. So for me, this is the net rate of heat transfer due to radiation at the bottom surface or into the bottom surface, which is why I have T surrounding minus T B to the 4. I don't know if this is true or not, okay? But we can figure out and come up with an idea. H bar is known to us. Alright, and so I just equate the convection and the radiation to get the temperature at the bottom. So I have sigma A epsilon this is H bar A T top minus T infinity. This is area at the top, area at the bottom. They need not be the same. In this problem, because I don't have any other information, I'm just going to assume them to be the same. H bar is known. Solve for T, B to the power 4. Comes out to be around 2300 Kelvin, I believe. 2341 Kelvin. Once you have this, just make use of the conduction equation, substitute and find the thermal conductivity of the plate. So Q convection is equal to Q conduction. This is the other surface energy balance at the top surface. And so I have H bar A T top T infinity. Because of the fact that there is no heat generation and so on, the temperature profile is linear. And so this is going to be A plate, A by the thickness, T bottom, T top. Area is the same. Thickness is given to us. This is 10 millimeters. T bottom is 234.1. T top is 460 Kelvin. That's given to us as well. Substitute solve. Okay, so this tells us a K plate. 2 point something. 2.21 watts per meter Kelvin. It's a nice refresher of all the concepts that we've seen. Okay? We looked at radiation networks in the problem I solved in the last lecture, so this is slightly more easier than that, but as I mentioned, this problem can be modified in many, many different ways, but nothing that we do not know. Alright, any questions on this? Yes?
What did you use for epsilon in the radiation?
What do I use for epsilon? That's a good question, so I should have given you epsilon as 0.6. Thank you. I should make a note of that fact. So epsilon of the bottom of the plate good catch. All right. Any other questions, please? And this is the broad nature of the problem that you can have in an exam. I mean, this same problem I could modify and say, okay, half of the plate has constant heat flux, the rest of it is constant temperature. The Nusselt correlation for half of the plate will be different, for the other half of the plate will be different. One has to account for these things. These are all just games that you play. That's about it. The fundamental concept is basic energy balance. Nothing else. Absolutely nothing else. Okay? Alright, next problem. Transient conduction. We haven't visited that in a very long time. We have the following setup. This is NMM. And then we are told that the thickness into the board or out of the board is 10 millimeters as well. Okay, so some kind of a box. I have a shaded area because that is going to be the contact resistance. So I have a contact resistance of 0.02 meter square Kelvin per watts. Remember, the units for thermal resistance in conduction and convection is Kelvin per watt. The unit for thermal resistance for radiation is 1 by meter square. Those two don't agree with each other, so you never use them in the same breath or in the same equation. Okay? And obviously, since this is given as meter square, Kelvin per watt, you have to divide by the area to get the actual resistance. Okay, so this is on a unit area basis. Then you have fluid. This is flowing at some rate which is given as 30 meters per second, and then you are told that the temperature T infinity is 1300 Kelvin. And then here are some information for us. One thing I forgot to mention, in the previous problem, Prandtl number, notice that the Prandtl number is defined as the kinematic viscosity divided by the thermal diffusivity. Okay, it's momentum diffusivity by thermal diffusivity. It's nu by alpha. So in our previous problem, the Prandtl number was actually equal to 1 because nu and alpha are the same. Okay, so here Prandtl number is given to us directly as 0.72. The thermal conductivity of the fluid watts per meter Kelvin. Then you have kinematic viscosity as 1.5 10 to the power minus 7. I believe it's 10 to the minus 7 or 5. Give me a moment. 10 to the minus 7, okay? And Nusselt number, you're told the flow is laminar all through. And Nusselt number 0.332 or Ex dimensions of this box are given to us. Here is what we need to do: obtain the heat transfer coefficient on the left side. So obtain average at x is equal to 0, which is this guy. And then we need to show that the Biot number is much less than 1. Obtain the Biot number. And once we obtain the Biot number, we need to do a couple of things. I want to sneak it in somewhere here. Maybe I'll just do it here. Obtain time taken to reach 1200 Kelvin for the plate. And then obtain the time taken to reach 0.99 times 1300 Kelvin for the plate. Okay. No mention of radiation, so that's good news. Not that we don't know how to handle it. There is always a possibility this side could be open to large surroundings and so on, so it's not a big deal. Okay? So let's start this problem by first of all calculating the average heat transfer coefficient. Flow is laminar throughout, and so we're calculating the h across the height of this plate essentially. Okay? To start off by calculating h bar, which is 1 by L, 0 to L. H dx, flow is laminar throughout, so this is just once again plug and chuck. So this is the length 1 by 100. Integral 0 to 100, 0.1. H can be written in terms of the Nusselt number. So this is the Nusselt number. By x kf dx. Substitute. So h bar is 1 by 0.1, integral from 0 to 0.1, 0.332. I'm doing the direct simplification. Reynolds number has a factor of a half, and the Nusselt number correlation, I have an x in the denominator here. So this is u infinity by nu to the power 1 by 2 dx. Integrate it to find it. So h bar is somewhere there. 75, let's say 75. 75, 76. See, at the beginning of the semester, what would have been done is you would have been given this h bar. Now we have the capability to calculate h bar. And the same story holds true for any kind of a geometry. As long as you know the Nusselt number correlation, these equations remain the same. Okay? So it doesn't matter if it is a complicated geometry or not, as long as you have the correlation. So that's done. And in order to show that this is a zero-dimensional conduction problem, zero dimension meaning that there is no spatial dependence for the temperature, it is purely a function only of time, we have to find out the Biot number, and then we have to show that this is less than 0.1. Okay, this is a standard procedure that we follow. Do not forget the definition of the Biot number. N Biot Okay, this is the overall definition of the Biot number. And it makes sense. If the thermal resistance to conduction is very, very small, it means that there is not much of a temperature change between the ends of the plates, between x is equal to 0 and x is equal to 10 millimeters. So we are looking at flow along the length of the plate. Now watch out. There is a contact resistance. To account for that, I draw this very short and trivial network. This is R convection. This is R double prime divided by area A, and then I have R conduction. This is T infinity. This is approximately T at x is equal to 0. X is equal to 10 millimeters. So this is the basic network that we typically have used for this problem if you are independent of time but dependent on space. What we want to show is that, okay, this R conduction is really so small that this temperature here is the same as that temperature, so there is no dependence on space, there is only dependence on time. Okay? So to do that, we have to change the definition of our Biot number. So for us, all of the stuff outside of T at x is equal to 0 is stuff happening outside. This is stuff happening inside. We want to compare the inside with the outside. So this is going to be our conduction divided by our convection plus our double prime by A. Does this make sense to everybody? And we would have obtained previously that the Biot number R conduction by R convection is H times L by K. Characteristic length by K of the plate, not the fluid. But now we have to do a slight modification. We have to include this contact resistance as well. It's kind of a pesky thing, but let's give it the respect it deserves. Alright, so let's start substituting, okay, for all these Biot number calculations. So NB, our conduction, remember, is L, or the thickness in this case, I'm going to call this as the thickness T. So T divided by K plate times the area, and K of the plate is given to us, I believe. I forgot to mention it, but it should be given. It's going to be 60. So K plate, 60 watts per meter Kelvin. Okay, that's given to us. So that's the numerator. Denominator, R double prime by A. Convective resistance is 1 by H times A. 1 by H bar in our case times A, because H bar is one that we calculated from. And as you see, that area cancels out everywhere. Substitute. I'm not going to go over the substitutions. This ends up being 0.0072. So this is great news. This is obviously less than 1.1. You can assume temperature is independent of space. In the exam, do not be surprised if your Biot number ends up being more than 0.1. You turn a blind eye to that and proceed. Okay? Alright, I have an interesting problem ready for you. So it's a word of advice. All we have to do is now set up the problem, and we just go on our merry way. So I have the following system. temperature at x is equal to 0 is the same as temperature at x is equal to 10 as a function of space. So this is now just a lumped system. It's just like a lump of clay with a temperature T as a function of time. Okay, that's why it's called the lumped system. Okay, because it's just lumped together. Everything is lumped together as a single variable characterizing the temperature of the body. Okay, and I have E dot stored is not equal to 0. E dot generated is equal to 0. It need not be the case. I could have E dot generated as non-zero. It's completely fine. And then I have some Q total, which I'm going to say is the following. Is delta T by R total, where delta T is T infinity minus T. And R total is this creature here. I'm taking all of these things and adding them up together. Okay, so that's going to be my R total. And that's R convection plus R double prime divided by A. Write the first law, and then we go on from there. E dot stored is E dot in, E dot out, E dot generated. This is the only equation worth remembering. Everything else comes from this. E dot G is gone. There is nothing coming out. Everything going in. So E dot n is equal to E dot stored. And with your permission, I'm going to take off this particular panel. Okay. Alright, so E dot stored is m times c times dt by dt. M, c. No longer partial derivatives, because we know that t is a function of only one variable, so this is a differential equation, ordinary differential equation. This is equal to t infinity minus t of t by r total. Or I can rearrange this to do the following. So this is MC R total dt by dt plus that's equal to T infinity, and you are given information on the density and the specific heat capacity of the plate. Here are the information for that. The density is 7,850. C for the plate is 430 kg Kelvin. So that mass times specific heat is density times volume times specific heat. What do we call that creature as? Tau. First order time constant from system dynamics. So tau is mc total, which is rho times c times the volume of the plate, which is the surface area multiplied with the thickness, is just a cuboid, and then r double prime by a 1 by h times a. And put in all these things together, you get around 14.5 seconds. I'll post all the calculations on carbon. A few of you wanted me to show you how to solve this using Laplace transforms. So with due apologies to those of you who may feel this repetitive, I'm going to solve this. Okay? So I have tau dt by dt plus t is t infinity. Okay? Laplace transforms, remember, I have t of 0 is T naught. This is the initial temperature of the entire plate. Let's assume that this is given to us as 300 Kelvin, 300 degrees Celsius. All of this information will be given to you. Okay. I take Laplace transform on all sides. So I have Laplace, Laplace, Laplace. Differentiate from the Lagrangian. Laplace of the first quantity is the following. It's tau times T of S minus T of 0. And then the other quantity is just T of S is equal to T infinity. So step input T infinity divided by S. And S being the S domain or the Laplace domain. I'm sorry, I forgot an S here. This is S times T of S. Laplace of X dot, for example. Right, and then I have the following now. So this is now an algebraic equation which can be solved using partial fractions and so on. I'll not go over that though. Okay. So from here I have T of S is T infinity S times tau S plus 1 okay, and then this is also multiplied by tau. I just rearrange everything. Took out the T of S, kept it as separate, or I write it in an even better way as T infinity by tau S times S plus 1 by tau, so that this is more useful to write in terms of partial fractions, and then plus, if I take tau as a common factor, it cancels with the 1 in the numerator, so I'm just going to have T of 0 by S plus 1 by tau. Okay, this is the Laplace transform of the entire equation. Then for the first part, we have to make use of partial fractions. Just briefly write it out. T infinity by tau by S times A by S by S plus 1 by tau. Multiple ways of solving this. You can do matching coefficients and so on. You'll end up getting A as T infinity and B minus T infinity. Okay. Substitute back. I have the following now. So T of S is T infinity by S. Infinity by S plus 1 by tau, and then T naught by 1 by tau. Or you can just take MATLAB and say Laplace. All of this will be done. Okay. You can also say I Laplace. It will take the inverse and give it back to you. You don't need any